I hope I'm in the right place. So good morning, everyone.
Morning.
And here are a whole load of examples of the chain rule. I'm not a person for memorizing things, so I wouldn't try and memorize all these combinations. I would think about it more in the way of there's a process going on here that creates the equation. We're essentially going to find partial derivatives of functions of more than one variable. And what makes this different from the rest of this week is that although the original function in this case is in terms of two variables, x and y, these variables are themselves also given in terms of another variable, or maybe variables, like whatever. So when you have a situation like this and you're being asked to find a derivative, it's almost always going to be in terms of one of these variables here. In this case, there's only t. So this here is an example of the chain rule formula for a function z in terms of x and y, where x and y are themselves functions of t. And the formula is basically the partial derivative of z with respect to x times the derivative of x with respect to t. And then you add the partial derivative of z with respect to y multiplied by dy by dt. If you look really carefully, do you see there's a kind of cancelling thing going on here? So this piece here is the contribution of the answer in terms of what x contributes to it. And this piece here is what y contributes to it. Now, if this had been a function of x squared, say, plus y squared plus w cubed, we'd add on a third term. We just say dz by dw and so on. So give you an example of what that looks like. Here's a formula function w in terms of three variables, x, y, and z. And x, y, and z are themselves in terms of a variable t. So if you want to define dw by dt, which is what you'd expect to be asked in this question, do you see it's made up of the contribution of x, the contribution that's with the, why have I put w there? Y, I should say y. Oh, it does. What am I doing? I'm scanning in the wrong place. Y, and then finally the contribution by z. Now, if you take that up one more level, imagine you've got a function z in terms of x and y are in terms of two other variables, in this case r and t. Then if you want to find the partial derivative of z with respect to, say, r, and the other one would be t, then there's two formula, but they're very similar. dz by dx, dx by dr, plus dz by dy times dy by dr. And you see that little cancelling? So that's basically the contribution that x gives to the answer, and this is a contribution of y. Now, if you find dz by dt, you see there's a very similar thing. So I don't try and memorize every single one of these. Can you see that if you gave me a function and it was in terms of three variables, and each one of those three variables was in terms of, I don't know, s and t, two other variables, I could generate the chain rule formula for any one of these derivatives. So I guess this is the only one I haven't kind of dealt with. Here's just a random example. Suppose z is a function of x and y. X is a function of now three variables, r, s, and t, and so is y. So you could be asked to find dz by dt, the partial derivative of z with respect to r, or the partial derivative with respect to s. Now, do you notice that the formula is really just these guys again? Isn't this a contribution with t, right, and y? So I'm going to try one that actually isn't a homework question, but just to take it to extremes. Suppose I had a function w, and it was in terms of x, y, and z. There it is. But x was in terms of r, s, and t. Y was in terms of course, they're all going to be in terms of the same three variables. Although they don't need to have all of them. You could have just that for one of them. Now, I'll take a volunteer. What would the chain rule formula be for this situation? What would the partial derivative dw dr look like? Don't want to know the answer, just want to know one of these guys, what the formula would look like.
Is it so partial derivative with respect to w of x times the partial derivative with respect to x times over t, and it's basically that, but replace the x with a y plus the same thing, but instead of a y you write it with a z.
Or a Z even.
Z, yeah.
Does that make sense? That you could actually, I mean, you don't get one as ugly as that, but couldn't you, theoretically at least, couldn't you do a chain rule for a function of 10 variables, where each one of those 10 variables was in terms of 4 other variables, right? Can you imagine all the permutations in the world? Now, you can't, and you shouldn't even try to memorize every possible permutation and the formula. Isn't it better just to try and see the process, how you would create it? So you're basically always going to say, okay, what's the contribution to the answer using X's? What's the contribution to the answer using Y's? And what's the contribution to the answer using Z? And I think that's a helpful way to look at these questions.
I have a question. How do you say that line you just wrote? Because I know how to write it, but I'm so bad at knowing how to say it.
Right. I would call, if I was just doing it with letters, I'd say dw by dx times dx by dr plus dw dy times dy dr plus dw dz times dz dr. If you wanted to be even more formal, you would say the partial derivative of w with respect to x times the partial derivative of x with respect to r, and then similar things for the other two, if that's what you're asking.
Okay, that's a lot more simple than I thought. Thank you.
Okay. So I guess really what we need to do is some practice, right? You know, practice makes perfect. A couple of people just turning up here. Seem to have lost Tim. So if you can bear with me just for a few seconds while I hide some windows. Right. So let's get some of these guys out of the way. I'm just going to hide these formula because I'm going to have to rewrite them anyway for each question. So I don't need them around in front of me right now. Okay, so suppose I have a function z and it's equal to the square root of x squared plus y squared. And x happens to be sine t and y happens to be e to the t, right? Keep it nice and simple to start with. In this question here, you would only be asked, because there's really only one question that makes sense in this, and that would be to find the derivative with respect to t. So I'd look at the combinations. That's okay, there's 2 variables and only 1 secondary variable. So the partial derivative of z with respect to x times the derivative of x with respect to t, and then the same basic thing, but using the second variable. Some of these are the partial symbol and some of these are the straightforward symbol. It's just been a little bit fussy, but if the function is only a function of one variable, its derivative is a real dy by dx. But if a function has more than one variable in it, it's a partial derivative. It really doesn't change anything significant. Of course, if I wanted to do this derivative, wouldn't I have to rewrite it for differentiation purposes as a half power? So the partial derivative of this guy with respect to x is multiplied by the power and then reduce the power by 1. Then you would multiply it by the derivative of x with respect to t. So in this case, it's cosine t. And then you add, oh, guess who forgot something, but caught myself. That is not the full answer to the derivative of this guy. What did I go and miss?
You forgot the 2n.
There we go. And then if I do the other one, it's going to be multiplied by the power, reduce it by 1, and then remember to differentiate this guy, in this case 2i, and then finish with the derivative of y with respect to t, and it's that guy. Now I'm going to do a little tidying up, really quite minor right now. That guy is going to go downstairs as a square root, and this fella and the 2 cancel, and you're going to get a y, you're going to get an e to the t, and this negative a half power comes down squares and looks like this. And now we're going to enter a kind of grey area. It really depends what WebAssign is comfortable with. But if this guy is a single variable, then I expect you to turn the entire answer into t's. If this guy over here is in terms of 2 variables, it's okay to mix and match all the different variables. So you don't need to tidy them up that much. Sally, what's your question?
I was gonna ask for the for just the generic formulas, specifically the ones where we have different variables. So with
Yes.
the partial derivatives of our x, y, and z, would that be based off of what variable wants us to take the partial derivative of, or is it always r?
I'm trying to think of what you're asking. I'm not 100% sure. So the guys that go first, right? The z's and the x's as we have here, they come from here.
Yeah, I'm talking about when like the x, the formulas, the x and y equal. I'm talking about like when they have an r, a t, an s.
Right. Well, if this had, say, 2 or 3 other variables, an r, an s, and a t, this formula here would not change. All you would have is 3 questions. You would be finding the derivative, partial derivative of z dt. Then you'd be asked to find dz dr, and then dz by ds, whatever the third variable is. So if the x and the y are in terms of more than 1 variable, this part of the formula really doesn't change. You just end up with 3 versions or 3 questions that you could be asked because of that.
Oh, so you just end up with 3 different iterations?
Yes.
Just each with the different variables?
Right. So they may ask you only to find one of them, but there are 3 answers. And the other question could have been dz by dr, and the third question could be find dz by ds.
Okay, thank you.
Right, Rosie, what's your question?
So in the problem, it's stated to find not the partial derivative, but the regular.
Yeah,
derivative.
and the only reason for that has been kind of lawyer-esque here is that if the variables, the x's and y's, are only in terms of 1 variable, this, strictly speaking, is a normal derivative, right? A calc 1 derivative. So it's a dz by dt. It doesn't change anything. I mean, the answer is still going to be the same answer, whether you called it partial dz by dt or dz by dt. It's just being nitpicky, but it is notation. So I'm trying to be precise in my notation.
Okay, so when you're writing down that initial formula to use, how do you know when to write the regular d?
Right. When do I write this?
Yeah.
And when do I write this? You will use this version when x's and y's, whatever the variables are, only contain t. You will write this version when the x's have at least 2 variables in them. So if it was a situation like that, you'd use a partial. When it's only 1 variable, you'd use a direct.
Okay, so the partial is if it's a mix. Got it.
Right. So far, so good. Now, back to this. If this has only got 1 variable, which it has, you really should, for style point purposes, make sure that everything's in terms of t. And I believe that's what WebAssign is expecting to say. That's definitely what I'm expecting to say. If you square that, you get e to the 2t. And then you take this fella, you get e to the t. That's an e to the t, I guess. And on the bottom, you get this fella. And again, this is style points. Since the bottom share a common denominator, I should combine them into a single fraction. And this guy is what, e to the 2t, and this guy is sine t cosine t. So that would be, in my world, the style point version of this answer. However, if you get a question where x is in terms of 2 variables or 3 variables, like maybe sine t plus r squared and e to the t minus 4r, if that happens, it's totally okay to leave your answer with x's, y's, r's, s, and t's, right? Just have the whole horrible mess of variables and don't really worry about the conversion.
WebAssign was okay with leaving the x's and y's. But if you're expecting us to substitute in the equations, that's fine.
You kind of cut off at the end, Sally. You were saying something about the x's and y's and leave it.
Oh, yeah, WebAssign's fine if you leave the x's and y's.
So WebAssign will say, okay. Is that correct?
Yep.
Yeah, WebAssign is an ugly, stupid formula, and it's giving you bad habits. So just do this for me. Make me feel happy, right? Do style points by that. Even if you have to write that in to make WebAssign happy, will you make sure that you do this? Because you realize you're not going to be using software. You're going to go to universities, a lot of you, and you're going to start doing stuff. And if you get into bad habits of leaving things kind of untouched, you're just going to get into all sorts of mess later on in your life when people say, well, you didn't really finish the question, did you? And you would be, what do you mean? Well, I mean style points. So it's a good idea to do more than maybe WebAssign needs right now, just to get into good form, right? Get into a good habit. Secondly, isn't that a much prettier answer when I tell you what T is? Can't you get the answer right away? If I left it like this and I told you what T is, will you see it's a little bit messier? I'm not sure if I've convinced you of that, but to make me happy, when this is a single variable, will you convert everything into T's? You might want to try it with T's and see if WebAssign accepts that as well. Because if it does, then I'll be really happy that WebAssign does recognize that that's a better version. Are we good? Okay. Let's just move on. Let's see what the next cell I'm going to pick looks like. Just scanning through homework, they're the easiest ways to find things. Oh, okay, how about this one? W is the natural log of x squared plus y squared plus z squared. And x happens to be 3 times sine of t. Y happens to be 4 cosine of t's. Okay. And z happens to be 2 tan t. I have names for things, you know, like I call things style points, right? I also have, as long as you do it to both sides, it's okay rule, which is a technique that you use in solving equations. I have a rule for this situation, and the rule is called just because you can doesn't mean you should rule. And it comes from when I was very young. I sang in the bath, and my mum used to bang on the door because I am a really bad singer. And she would say, just because you can sing doesn't mean you should. Just because I could do this question and find, as they want us to do, find the derivative with respect to t. I could find the answer that way. But just because I can do it that way doesn't mean that I should. Because I am going to do something to make this a little bit easier. Isn't this the same thing as x squared plus y squared plus z squared to the power of half? Would you agree? Square root is a half power. Isn't the rule in logs that you can pull out a half power like that. Now let's look at the original question. Do you really want to differentiate that question with respect to X, Y, or Z? Do you want to do that? And probably your answer is, oh God, that's going to be a chain rule inside a chain rule, and then I have to deal with some squares, and I'm likely to lose something in that process. Would you agree that this is a much easier function to differentiate? Are we good? I'm worried I've lost everybody. I'm not hearing anything. Somebody say hi or something, just to make sure I'm not talking to myself. Oh, we're good. Okay. Are we comfortable with this as a process, right? And so I'm going to use our formula for calculating the derivative with respect to W. So we differentiate with X and then dx by dt. We differentiate with Y and then dy by dt. And then we differentiate with Z, dz by dt. Okay, if you differentiate this function with respect to X, a half log of something gets you half 1 over something times the partial derivative of this with respect to X, which is 2x. So that's that guy, followed by dx by dt. And if you differentiate this guy, you get 3 cosine t's. Now, because this thing is so big, I won't have enough room to squeeze it in here, so I'm just going to put plus underneath. I know what the derivative of dw by dy is. It's a half 1 over x squared plus y squared plus z squared times 2y. And then I differentiate 4 cosines, which gets me -4 sines. And then I do it one more time. And with respect to z, we get 1 over this guy times the partial derivative of this with respect to z, which is that guy, times 2 tan t. What's the derivative of tan t?
Would that be secant squared t?
Correct. So
You have a -4 cosine t in your notes, sir.
oh, this one here should have become, thank you, well caught, -4 sine t. We good on that? Okay, let's see what the answer looks like. If I can try and at least make it vaguely pretty. The 2 and the 2 cancel, so I'm going to have an x with a cosine t. This guy and this guy is going to cancel. It's going to be a y in this guy, so I'm going to be a 3 there. Got it. This guy's going to have a negative, a 4, a y, and a sine t. And this one, that's going to cancel. I'm going to be left with a 2. I'm going to have a secant squared t. And everybody shares the same common denominator, which is basically x squared plus y squared plus z squared. And if I replace the x's with sines, I now get 3 sine t cosine t. If I replace the y by this fella, I get, well, what do I get? I get 3 times 3, that's 9. I get 4 times 4, which is 16. What's that going to get me? Cosine and a sine, so that's sine t cosine t. And there should be a z here, isn't there? And there should be a 2z there. Right, so that's 2 times that. It's going to get me 4 tan t secant squared t all over this guy. 9 sine squared, 16 cos squared, and 4 tan squared. What an ugly looking answer, but they may get something out of it. That guy and that guy are the same, so I can get -7 of them. If you do a tan and a secant, you really don't get anything worth talking about. There's nothing I can say. There's really not a lot on the bottom, so I'm just going to dot, dot, dot. In all intents and purposes, that is one ugly answer. I can't make that. Yeah, I was kind of suspecting or hoping that these things here would work with a nice trig identity and might turn into something nice. But the only thing that even vaguely behaved well together were those two terms, and that's not a lot. Big question, a lot to it. Let's try another one. Let's do a two variable one, right? Let Z be x take away y to the power of 3. And x is going to be st, and y is going to be s squared t squared. And we're, in this question, going to be asked to find these two different answers. Okay. I don't really want to do both of them, so I'm just going to pick that one, I think. So it's going to be the partial derivative of z with respect to x multiplied by dx by ds, and then the partial derivative with respect to y, and then multiply it. This guy is 3 times x minus y squared. Technically times 1, but it's hardly worth writing that. That's the first bit. And then this guy is the partial derivative of this with respect to x, which happens to be t. And then you add, well, when you differentiate this with respect to y, you get 3x minus y squared times a -1, so you get that. And differentiating this with respect to s, you get 2st. So it looks like I'm going to have 3 lots of x minus y squared t plus, well, it won't be a plus because of that, and 2 and 2 gets me 6. So it's -6 x minus y squared times st. Now, when these are 2 or more variables, it's okay to leave the x's and y's and t's and s's, right? You don't need to change anything, but you still should do style points. Is there anything you can do to that expression to make it look pretty?
Factor out an x minus y squared t. And also a 3.
Quite a lot, really. And that, I believe, leaves you with a 1, and that takes out a -2, and there's still an s. Would you agree that's just slightly prettier? And that's it.
Would that
Yes.
be 2st squared for the y?
Did I screw up one? Which one?
The terms that you're doing the partial derivative of y with respect to x.
Oh, this one
as-
here? Oh,
Yes,
there's,
yes,
yeah,
yes,
so
yes.
this guy should be a square there, shouldn't it? There, you're right, missed it. Well, the fact you caught it is a good sign because it means you know what the heck's going on. Are we good with that one? Any questions? Okay. Let's up the food chain. This is a version of question 6. Z is e to the r cosine theta, and r is s times t, and theta is the square root of s to the 6 plus t to the 6. And I'm only going to find, I don't know, I'll do that one, right? Whoops, one of these variables. I'll do that one. So we're going to do the derivative with respect to the first variable, which is r, the r by dt. And then we're going to do dz by d theta, and then do d theta by dt. I think I'll put it over here, I'll need room. Right, you differentiate this with respect to r, and you really don't get much, almost unchanged. And if you differentiate r with respect to t, you get this. That's quite nice. Now, if you do it with respect to theta, you're going to get, well, I didn't know until it happened, so you're going to get a negative sine theta. And differentiating that thing is a pain because it's really going to have to be a chain rule. So it's 1/2 s to the 6 plus t to the 6 to the negative 1/2 power. And differentiating this guy with respect to t gets you 6t to the 5. So we're going to have an s and e to the r cosine theta. Subtract that, and that gets me 3. I get a t to the 5. I get an e to the r. I have a sine theta. And I believe that's a t. That guy left over. I could probably pull out an e to the r as a common factor, and that would leave me with that as my first term. Take away 3 t to the 5 sine theta, and I probably should call that a square root on the bottom. And that's pretty much the best I can do with style points. Any issues with that question or any omissions that I may have done? Are we good?
Makes sense to me.
Cool. Let's move on. W is going to be xy, yz, and zx. X is going to be r cosine theta. Y is going to be r sine theta. And z is going to be r theta. So W is a function of 3 variables, and each of these 3 variables are themselves a function of 2 variables. And we'll pick, which one do you want, R or theta? I don't care. Which one should I do? dW dr, partial derivative with R, or partial derivative with theta?
Theta.
Theta gets a job. So differentiate with X, and then that guy. Differentiate with Y, then that guy. And finally differentiate with Z. You get that guy. And I won't really need to do too much tidying up because there's 2 variables here. So if you differentiate this fella with respect to X, you get a Y, a nothing, and a Z.
I'm gonna be honest, I don't really know much about this stuff.
Say again, Tim?
Sorry, I thought I had my mic muted. I got a call from Mark.
Oh, okay. I'll mute you so we can't hear you have your call. Right, now if you differentiate this with respect to theta, you get negative r sine theta. And then the middle term, partial derivative with respect to y, you get an x and a z, and then you differentiate this, and that gets you an r cosine theta. Of course, I don't have enough room for the third one. If you do a z, you get a y plus an x, and then you differentiate this fellow with respect to theta, and you get an r. So, interesting. I could pull out an r, I guess. Not much else I could do. I could go y plus z sine theta with a negative in front, plus x plus z cosine theta plus y plus x. Yeah, it's very ugly. I don't think I could make it any prettier.
How did you get the y plus z and the x plus z and the y plus x? Is that because you're doing product rule?
No, all I'm doing is differentiating this with respect to one of the variables. So for instance, if I wanted to find out what that was, which is the term that goes here, you differentiate partial derivative of this with respect to x. Well, xy is like 5x, you just get the y term. This guy here doesn't have any x's in it, so you get 0. And this guy, when you differentiate it, partial derivative with respect to x, all you get is the z. So that's where the y plus z term came from. And then there's another one, this guy, and that ends up being x plus z. And if you do it again with the last one, that gets you y plus x.
Okay, got it. Thanks.
Got it? Right. I don't have any, just be careful, because I know WebAssign can be really weird at times, and especially if the answer is ugly like that. But I think it's versatile enough to know different combinations of the same function. I haven't done a fraction. This one is like 11. N is a function p plus q over p take away q. P is in terms of 3 variables, u, v, and w. And so are the other 2. Okay, so I'm going to find, let's find that one. So it's going to be let's find that one. It's going to be this fella. So it's actually only got 2 terms to it. The first function is in terms of p and q, which is those 2. And we're only interested in the u variable from here. But I do have to do a partial derivative of a fraction, which is not going to be particularly clean. So let me do it over here. If you want to do a derivative of a fraction, and the variable that you're interested in is in the top and the bottom, then you're really going to have to do the quotient rule. So essentially f dash g, take away f of g dashed over g squared. And the top is going to be f, and the bottom term is going to be the g. So if I differentiate the top with respect to p, I get 1. You then multiply by the untouched bottom. Take away, you leave the top alone, and then you differentiate the bottom with respect to p, and you get 1 again. And then the bottom term gets squared. So what I have is p take away q, subtract p take away q. It looks like I end up with negative 2q when I'm finished. So return to here. Yes.
Was it supposed to be, for the quotient rule, was the second term been p plus q? Or did you distribute your negative?
I distributed my negative. So negative this is negative p, negative q. Right, taking away a p plus q, I've distributed the negative. So this guy is negative 2q over p take away q squared. Now, if you differentiate p, which is this one, with respect to u, you don't get much. You just get 1. Now, if you go through this same process, but you do a partial derivative with respect to q, it's going to look something like this. F dashed g take away f of g dashed over g squared. With respect to q, then, the top derivative is 1. You leave the bottom alone. Subtract, leave the top alone. And then differentiate the bottom with respect to q. You get negative 1. And then square the bottom. So what do I get on the top? I get p minus q. That becomes p minus q because they cancel out. P minus q add p plus q. So you get 2p. And if you differentiate q with respect to u, so if you take the partial derivative of this function with respect to u, you get a w. So it looks like we're going to get negative 2q plus 2pw all over this guy. Does that look okay? Any questions about that one? Or can we move on? Looks like we can move on. Oh, and I didn't do some. I didn't realize it until I had another look. In this question, you are told U is 4, V is 3, and W is 7. So you're actually not finished. You're expected to find out what the answer is, what this is equal to at that point. Well, it's a bit messy. I can see that right now. Because don't I need to know what P and Q are in terms of these variables? I already know what these are. So what does I get? What do I get for Q? So let's see, it's negative 2 times Q. Q is V plus UW. So what that would be? It would be 3 plus 4 times 7. So it's 31. So it's 31 goes there. Add 2 times P. Well, what do I know about P? It's U, which is 4, plus 3 times 7. So I believe that's 25. So P is 25. Times W, which is just 7. All over P take away Q squared. 25 take away 31. Squared. So I get negative 62 plus 350 all over negative 6 squared, which is 36. And I'm getting bored with this question. So how about dot, 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 and you can make it look pretty yourself later. Are we still good?
Yeah.
Yeah, okay. So let's show you something that you haven't seen. I'm going to show you an application of the chain rule, or at least a formula that came from the chain rule. Can you remember Calc 1? Having to differentiate what was called an implicit equation. Can you remember that stuff? Can you remember how ugly it was algebraically and very clunky and took a long time? Because didn't you have to differentiate everything here with respect to x and then solve for dy by dx? Remember doing all that stuff? So, wouldn't it be nice if there was a different way to do it? And here is the formula that chain rule gives us. And if you're wondering who is F, that whole thing is your F. So there is a whoops. This one is one of those questions you probably should memorize the formula. And what we got here is that for this Calc 1 question, its derivative dy by dx is equal to the partial derivative with respect to x divided by the partial derivative with respect to y, and then you stick a negative in front of it. Well, if you differentiate this with respect to x, you get 2xy cubed. If you differentiate this with respect to x, you get the sine of y. If you then differentiate this with respect to y, you get 3x squared y squared. If you differentiate this with respect to y, you get 2x cosine y, and then just remember to stick a negative in front of it. Did you see how quick solving that problem has now become? If you had to do that by the method of Calc 1, wouldn't that be, I don't know, 4, 5, 6 times longer? Sally?
So the number at the end, that 10, does that affect the answer at all?
No, as long as it's a number. If it's an x, you bring it over to the left-hand side and make it part of the f function. Isn't that cool? Wouldn't you like to have known that formula when you were in Calc 1? Because wouldn't you get the answer in less than 30 seconds as long as it wasn't too awkward looking? I'm not going to show you.
I just
Yes,
want to
sir.
know why you kept that a secret in Calc 1.
Ah, you know, a little knowledge is a dangerous thing. To be able to do this, don't you have to understand what partial derivatives are, right?
Well, I'm in the Navy, so I push that I believe button a lot.
Okay, I hear you. Well, one of the reasons, there's lots, but one of them is that you're not ready for it. If I told you about partial derivatives in Calc 1, wouldn't you end up doing partial derivatives in lots of places you were never meant to do it with? Right? Oh, I like this. I'm going to use it all the time. I'm going to use it even when I shouldn't use it, right?
Well, yeah, I mean, that's also like a Navy habit, you know?
Oh, they tell you stuff because you know, this is what you do, and then you try doing it in places where you shouldn't be doing it. Yeah. So that's what it is. There are lots of cool things that you don't know because we haven't told you yet. I'm going to tell you a little secret, not a really big one. Do you know the sine function? Right. That guy. Oops. Goes back down again. Right. Haven't you been told that the sine function only has values between 1 and -1? Would you all agree that is a pretty obvious thing, right? It never gets bigger than 1. It never gets less than -1. That is true. I'm not saying it's not true, but it's only true when x is a real number. If x is a complex number, remember complex numbers like 3i plus 2? The sine of x can be any number. It is possible to get a sine equal to 2, but you have to use x as a complex number to make it ham. In fact, complex numbers or sine functions, all we're really looking at when we talk about it in 142 is we're looking at the sine function as it hits the XY plane in the three-dimensional world. And when it hits the XY plane, its shadow looks like that. But there's a third dimension, the Z, and it lives up here as well. And when it lives up here, the sine function can be a lot bigger than 1 or -1.
Is that because it's a coil turned sideways, right?
A helix,
A helix, yeah.
yes.
Turned si- You're just
Yeah.
looking at it in one dimension.
Well, technically we're looking at in 2 dimensions, right?
Yeah.
But if you visualize the third dimension is where the complex numbers are living, you can see that the sine function takes on a totally different look to it. Now, can you imagine why we didn't tell you that in trig? Because then wouldn't you be using it in places you shouldn't? Like you'd be trying to solve equations, sine x equals 2, and you would wonder, you know, it should be equal to 2 because you told me it could be equal to 2. The only thing you forgot was that it's going to be a complex number. I can't tell you off the top of my head what it is, but it'll probably be something like the sine of pi I.
So would that represent something like the amplitude in radio waves? Because I know, yeah, your frequency, that's your sine wave there.
No,
Well, actually, your frequency is to do with how close these guys are, and
It
your
represents-
amplitude is the height. So no, it wouldn't be
represents
that.
mechanical motion. It represents mechanical motion. So if you have a generator,
Right.
the generator rotates in a plane, in an XY plane, and it generates as a function of time. And then let's say that you had a 3-phase generator, the XY is broken down into 3 phases, and the power is sent down 3 wires and then recombined in a motor. So basically you're taking a 3-dimensional rotational function, turning it into a 2-dimensional sine, cosine function, transmitting it, and then assembling it back together in a three-dimensional. I know it's kind of weird to understand, but a guy explained it to me and it made perfect sense. A physicist explained this to me.
Okay.
So that,
yeah, although it doesn't, it's not your explanation that's the problem. It's my lack of engineering expertise. You realize that the real world applications of calculus is going to be in a 3D world, right? That's what we really live in. When you do your Calc 1 and your Calc 2, isn't most of the world kind of reduced to X's and Y's, right? X, Y plane. Occasionally you did a little rotation stuff, but not much in the 3D. Do you see that we're now moving on to more real world? And when you move on to the real world, you have to introduce at least 3 dimensions, right? X, Y, and Z. I think what you're trying to tell me here, Martin, is that when you look at how something works, it can very often be a 3-dimensional thing, but sometimes for simplicity, you reduce it to a 2-dimensional situation. But at the end, you go back to the real world, which is a 3-dimensional thing.
yeah, because you can't analyze something always in 3D because of the complexity.
Exactly, yeah. So it makes sense that you would simplify a situation to be able to deal with it, but when you've got the solution, you then return to the real life. Okay.